All right. In this module, we will talk about axioms of probability. So to start talking about axioms of probability, we will first define something known as a probability space. So first, let me define the key elements of this, and then we will work out a simple example to position these abstract notions. So we'll start with something called as space. So space or sample space. Sometimes it's called space, or sometimes it's called the sample space. It's denoted by a set S, and sometimes in other textbooks or places you will see a sigma, a big sigma. What does this denote? It denotes the set of all possible outcomes in your experiment. So S or sigma will be a set. So what I want you to remember, it's a set of outcomes, set of all possible outcomes. Elements of S, individual elements of S, will be the individual potential outcomes of that experiment. Subsets of S will be events, and we will talk about that. And of course, a subset of S is a null set. So null set represents the impossible event, an event that never occurs. Okay. So let's set up all of these and view them through a simple example. So suppose we run the following experiment. We roll a 6-sided dice. So let's write down what would be the sample space for this experiment. So if you roll a dice which has 6 numbers written on them on 6 sides, then the set of all outcomes is either you will see a 1 or 2 or 3 or 4 or 5 or 6. So these are all the set of all outcomes. Okay, so this is set of all outcomes of this experiment. Okay. Elements of this set are outcomes. Okay. Now let's think about events. What is an event? So if I describe to you an event in words, so let's say the event of observing an even number. So we can describe this event through a set. Let's call that event as a set E1. It will contain those outcomes which correspond to this event of observing an even number. So what are the even numbers in the set? 2, 4, and 6. So this is an event. An event is a subset of the sample space S. Hopefully that is clear. This is not a unique event. You can define other kinds of events. For instance, you can say, well, how about the event of observing a prime number? We can describe through another set. So we will look at all elements in the set S which are prime. So 2, 3, and 5 are prime. So this is another set representing this event of observing a prime. Okay, hopefully that is clear. So if we denote A as some event, okay, what we're going to denote in the probability space, we're going to assign it a number. We call it P of A. Okay, this P of A will denote the probability of an event A. Okay. All right. Now, so what is a probability space? Probability space contains the following. It contains a sample space, which has elements. Subsets of S are events. Okay. And then what we will be interested in is assigning a number to them, which will represent the probability of an event occurring. Okay. Now, what are probability axioms? Now we are ready to define the probability axioms or the rules that we should follow when assigning these numbers. Okay. So here are the probability axioms. Let's write them one by one. So here are the axioms of probability. So I'm going to write 1, 2, and 3. There are 3 axioms, and you should remember them. The first axiom is probability is non-negative. Okay, so I'm going to write mathematically on the left, and then the interpretation in words on the right. So what this means is probability is always non-negative. Okay, that's the rule we have to follow. The second rule we'll follow is the probability of the sample space is 1. Okay, which means that sample space is a certain event. Sample space is a certain event. And when I say certain, I mean it occurs with probability 1. Okay, that is, it occurs with probability 1. Okay. Of course, this makes sense because if you roll a dice, what's going to happen? Any one outcome out of these 6 will show up. So you will always see something from the sample space. So sample space always occurs. So that's why it's a certain event. Third axiom is the following, that if A and B are such that the intersection of A and B is the empty set, then the probability of the union must be the sum of the probabilities of A and B. Okay. So in words, what does this mean? It means that the probability of the union of two mutually exclusive events is additive. Of course, you remember A intersection B is the null set, means that they are mutually exclusive or they are disjoint, right? So if you have two events which are disjoint and you look at the probability of the union, the probability, it should be equal to the probability of A plus the probability of B. So bottom line is the following. We want to assign numbers or probabilities to events which should follow these 3 rules. These are the axioms of probability. Okay. We'll work out an example in a bit. But first, let's see a very simple fact that we can actually determine using these axioms. So the fact that I'm going to prove using these 3 axioms is the following. So I'm going to write that in a box, which is worth remembering, is the following fact. The probability of any 2 events, A union B, is the probability of A plus the probability of B minus the probability of A intersection B. Okay, so this is a general fact. Okay. The way you can think about it, or the interpretation, is the following through a Venn diagram. So imagine I have, this is my, let's say, sample space. I'm going to draw it in a rectangle. Okay. And then I have 2 events represented by these bubbles, A and B. Okay. So if I were to ask you to write the union of A and B, you would say, well, I can write it as, so let's say this shaded part is A, and then I can draw this part as the intersection of A and B, the part in pink, and the stuff in this color is whatever is in B, but not in A, right? So if you think about it, A union B can be written as the part in black, the shaded black, plus the entire B, but then I have to subtract out the common part once because I don't want to count it 2 times, right? Okay. So we can prove this result very easily using the 3 the probability axioms that we just stated. Okay, so let's try to see the proof of this result. So we're going to take A union B and write it as follows. So I can write A union B and B as follows, and write it as intersection of A complement with B. So try to convince yourselves, what is A complement? A complement is everything that sits outside A, right? This yellow part is A complement, right? So if you take the intersection of A complement with B, what will you get? You'll get the stuff in orange, right? Okay, and that's going to be basically the additional part that you need to append to A to get A union B, right? So now, if we take the probability of this union, it's the probability of A union A complement intersection B, right? We have not done anything wrong so far. Now, what does the third axiom say? Third axiom says that if 2 sets are mutually exclusive, then the probability of the union is the sum of the probabilities. So we can apply the third axiom. So from here on, we apply axiom 3 it says that using this axiom, I can write this as probability of A plus the probability of A complement intersection B. Okay. Okay, so let's call this as our first step. Okay. What we're going to do next is then we're going to break down B as follows. So we can write B as intersection of A with B, the part in pink, union A complement intersection B, the part in orange. Right? Hopefully that is clear to everybody from this Venn diagram. B can be written as union of two disjoint components, a part that intersects with A and a part that intersects with A complement. Right? Then we're going to look at the probability of B and apply the third axiom. Because these two, pink and orange, are mutually exclusive. So therefore, when I take the probability, what I'm going to get the sum of the two probabilities. Hopefully that is okay. Right? So if I write this as equation number 1 and I write this as equation number 2, then from 2, we can write probability of A complement intersection B as the probability of B minus the probability of A intersection B, right? And then we can take this guy from here and plug this guy in 1. We obtain, what do we obtain? We obtain what we wanted. So if we rewrite 1 starting from the left, we get PA union B is P of A plus, remember, PA complement B right from above. But then this becomes P of A plus this guy, which is P of B minus P of A intersection B, right? And that's what we wanted to prove, right? So that was our goal of proving this result. So what I wanted to show you here is essentially just a very simple illustration of how to use these probability axioms. Specifically, this proof involved just invoking the third axiom 2 times. Okay, getting a little bit more comfortable. So having defined this, let's now move on to event axioms. Okay, so the entire probability space has 2 types of axioms. One is probability axioms, which just tell us that what kind of probability values we can assign to events. And the next part will be something called event axioms. So let's talk about that. And we'll work out a few examples when I'm done defining. Okay. So let's see where we are. Okay. So if you if you think about events, what are events? So events are subsets of S, right? Remember, this is how we define events. Okay. So we define the set of all subsets of S and give it a name and call it F. So F is the collection. So think of F as the collection of all possible events. Collection of events, all events. Okay. Hopefully this is clear, and we'll see in a few examples. Okay. So we're going to define 3 event axioms. I'm going to call them E1, E2, and E3. Okay. So first axiom is that sample space S or sigma must be an event, which means S must be a subset of the collection of all events, or sigma must be a collection, must be in the collection of all events. Okay. The second event axiom is that if A is an event, then the complement of A is also an event. Okay. Finally, if A and B are events, then A union B must also be an event. Okay, sounds good. Now, if my collection of events F satisfies all these properties, if F satisfies all the above properties, all the above three properties, E1, E2, and E3, then we call this as we give it a name in probability theory, we call it a Borel field. And sometimes you will see a sigma algebra or a Borel sigma algebra. Again, don't worry about these names here. Just think about it as I think remembering Borel field is something which is good to remember. Okay. Now, with all this in place, we can fully define a probability space. So to define a probability space, what do we need? We need three things. So I'm going to create a red box here. So a full description. So the full description of a probability space has three things. It has a space, sigma or S. It has F, and it has an assignment P. Okay, so let me explain each one of them. This corresponds to the sample space, set of all outcomes. F corresponds to set of all possible events, satisfying the properties E1, E2, and E3. P corresponds to assignment of probability values to events, okay, which must satisfy the axioms, probability axioms 1, 2, and 3. Okay. So with all these three things in place, this will describe you or give you a full description of a probability space. Okay. So now it's about time we see some examples and move away from the abstract world. Okay, so the remainder of this module, we'll look at a few examples to crystallize these concepts. Okay, so let's take an example. Suppose I have a sigma or S as A, B, C, and D. Okay, so I have 4 elements in my sample space. Okay, let's say I want to create a field, a Borel field. Okay, so here is a Borel field. Of course, a simplest Borel field will contain the set of all possible subsets. Okay, so for example, I can do the null set, the set S, the set A, B, C, D, A and B, A and C, and so on and so forth, right? Now, how many guys are there? How many subsets are there in this set? It's 2 raised to power 4, remember? Okay, so the number of sets in this field, so this is, let's call it a field F1. Okay. Interestingly, there are smaller fields out there which satisfy all the 3 properties E1, E2, E3. Okay, so let's take an example. So suppose I want to create a field F2, which, of course, it must contain the set S. Okay, if it contains the set S, it also must contain the complement of the set. Remember, which axiom is this? It's the second axiom E2, right? Okay, so if I have a field F2 which has S, it must contain the null set as well. Okay, it turns out this is a field. So this is a valid Borel field. In fact, this is the smallest valid Borel field. Okay. So F2 is the smallest valid Borel field, and F1 is the largest valid Borel field, which contains all possible subsets of S. So you can ask this question: are there something intermediate in between, which we can also call that as a Borel field, which satisfies E1, E2, E3? Turns out yes. For example, let's start with creating a field by putting S and phi, we have to do them. Let me now include the element A. If I include the element A, what else do I have to include? By the second axiom, if this is contained in the field, then the complement of A must also be contained in the field, right? What's the complement of A? The complement of A is B, C, and D, right? So this is S minus the set A, right? So I include that in the field. Then I have to, let's see, what else do I have? So I have satisfied event axiom E1. Have I satisfied E2? S's complement is phi is contained. Phi's complement is S contained. A's complement is this contained. BCD's complement is A contained. Okay, so event axiom E1 and E2 are satisfied. Let's see. Do we need to put anything else in this field to satisfy the remaining axiom E3? E3 says if A and B are two events, then A union B must also be an event. Okay, let's take union of all possible guys in our set. What is the union of S and phi? It's S. S and A is S. S and BCD is S. So we are good. What is the union of A and BCD? It's ABCD, which is S, which is already in the set. So which means we can safely say this is also a valid Borel field. Okay. So hopefully this gives you an example of a Borel field. So let's go on to actually assigning numbers to these probabilities. Okay. Let's take another example. Simplest example is, say my sigma or S is two elements, heads and tails. Okay. And I'm going to construct a field which is phi, the empty set, the set S, which is heads and tails, then H and T. Okay, so this is my field, right? Now, what I'm going to do, I'm going to assign probability values. So I'm going to assign probability to the set H as, let's say, 0.3. And the probability value to the tail element as 0.7. Okay. Right. So let's see. What is the probability of S? The probability of S is the probability of the set H comma T. Now these are mutually exclusive events. From one of the probability axioms, what do we get? This must be equal to the probability of H plus the probability of tails, right? Which is 0.3 plus 0.7, which is equal to 1. Okay? So the probability of the sample space is 1. Okay? The probability of the null set is 0. Right? So all I've done here is on the left-hand side, I'm showing you assignment of probabilities to all the events in my field. Sounds good? So hopefully this is clear. So let me just rewrite the field for this simple coin toss experiment. I have the null set, I have the sample space, I have heads, and I have tails. Okay. Null set has assigned, so the probability values to these events are 0 to the null set, 1 to the sample space, 0.3 to the heads, and 0.7 to tails. Now keep in mind, these 0.3 and 0.7 numbers are arbitrary. I could assign in principle, let's say a value p between 0 and 1, and then q to this guy, and then I would need to make sure that p plus q must be equal to 1, right? To ensure that the probability of the sample space is 1. Okay. All right. Let's take another example. Now, suppose I do an experiment of tossing a coin 2 times and recording both outcomes. So what's my sample space? Let's first write down the sample space. So my sample space will be what? So I toss a coin, I will see heads and heads in both the tries. Heads in the first one, tails in the second one. Tails in the first one, heads in the second one or tails on both the outcomes, right? So this is my sample space. What are the number of outcomes? Number of outcomes is 4. Okay. If I were to ask you, write down the largest sigma, the Borel field. So your Borel field will look like what? It will be the null set, the sample space, HH, HT, TH, TT, then HH, HT, HH, TH, and so on and so forth. How many elements will be there? If you look at the most expansive Borel field, 2 raised to power 4 elements, because the number of outcomes was 4. So this Borel field will have 16 elements. And what are these guys? These guys correspond to events. So these are events. Okay. So for example, to make it a bit more, giving an example, we can ask, the event of observing a single head in both tosses. How will I describe this then? So single head in both tosses means that the first outcome could be a head, but then the second will be a tail, or the first outcome will be a tail, but the second will be a head. Right? These are the only 2 ways I can get a single head in both tosses. Right? So this is an event. Hopefully it's clear. And if I were to write, what's the probability of this event? The probability of this event is the probability of this set of outcomes, HT and TH. Now, by the probability axiom, okay, which probability axiom was it? Let's go back. Third probability axiom. By the third probability axiom, since these are mutually exclusive outcomes, then this is going to become P of HT plus P of TH, whatever values I have assigned to these individual guys, right? Another example of an event could be, so let's say the event of observing a head only on the first toss, right? In this case, I will get only on the first toss and not on the second one. So this will be just HT, right? And so the probability of this event will be just the probability of this set, HT. Right? So to fully describe this experiment, what I will need to specify, I'll need to specify what's the probability with which this outcome shows up. So for example, let's say I specify the numbers 1 by 4, 1 by 4, 1 by 4, and 1 by 4 to all these 4 outcomes. Then I can, work out these guys. So this thing will be 1 by 4 plus 1 by 4. This will be half. And this thing will be 1 by 4, right? Okay, so we'll stop here. Hopefully this gives you an idea of how to take the probability axioms and the event axioms and work out in a specific context. Thank you.